Roberto. So I will be covering 4 different techniques: fused deposition modeling, and micro-dispensing, ink, and polyjetting. As you see as I go through my slides, they're generally descriptive of the nature of the process, and as Roberto pointed out, there are certainly some advantages to each methodology and also some challenges in terms of using microwave applications. Starting with fused deposition modeling, which is also referred to as fused filament fabrication. There's a filament of thermoplastic that is fed through a heated nozzle, which you can see in the figure. And the nozzle temperature is typically 200 to 400 degrees Celsius or so, enough to have a molten material. The technique, its name, is that as the material is deposited onto the printing bed or the layer being deposited onto, it actually fuses with the previous layer of thermoplastic. And the key things for RF and microwave applications is the minimum layer thickness and also the just the precision of the stages that are used to locate the material very precisely. So on the high-end FDM systems, it's typical to have micron resolution and minimum layer thicknesses on the order of 50 microns to 30 microns or so. And this is really important because it addresses the issue of surface roughness or surface profile, and that has a noticeable effect on the of microwave devices, especially as you go up in frequency. And pretty much regardless of the lightness that you achieve, you're still going to have some kind of filament pattern in the surface, and that can also lead to anisotropic effects. Materials, as I mentioned, they're all thermoplastics, and typical commercially available materials have electric constants in the range of 2 to 3.5 or maybe to 4. And one very thing about FDM and the thermoplastics for microwave that you can achieve very low loss tangents on the order of 0.002. Recently, there have been some custom materials developed using ceramic microparticles with thermoplastic material to form a composite, and electric constants in the range of 5 to 6 have been demonstrated, and up around dielectric constants of 10 using ceramic nanoparticles, having the low loss tangent values. The device you see in the lower right-hand corner is achieved using FDM. See these beam structures with sizes on the order of 0.5 millimeter or so. I'll discuss is called micro-dispensing, and as you can see from the photograph here, it can use a nozzle which is very similar or identical to the except that in this case it's a paste that's forced through the nozzle using pressure. And depending on the nozzle size and the material that's being used and the straight or the material that's being deposited on, it's possible to achieve line widths of around 25 microns and print heights of similar dimensions, about 25 microns. So this essentially can be considered like a thick process almost, but it has the direct write capability. Things about micro-dispensing is because it does use materials from the thick film industry, there's a very wide range available from materials, controlled resistance, and highly conducting silver paste, for example. It's possible to have a very wide range of viscosity. Some viscosity of 1 is essentially like water, and up into the million range, that's a relatively thick paste that can be pushed through the nozzle. The device you see in the lower right-hand corner is actually made using a combination of FDM to use the substrate, and this is a demonstration of using micro-dispensing to create the interconnects. And this device and similar ones are described in the paper in this view, which is noted at the bottom of the slide. So ink, of course, the process it's very familiar to many because it's essentially the same technique used in low-cost printers, which many people have at home. Of course, for advanced additive manufacturing, there's some special capabilities in terms of types of materials that can be used and the feature sizes. So ink comes essentially in 2 different flavors. One is illustrated here. It's referred to as continuous inkjet. There is a stream of small droplets that are pushed through the ink head, and then the droplets are either allowed to fall onto the surface and create the print, or collected and then recycled. So here, dispensing as a thick film process, it's helpful to think of inkjetting as a thin film process. And in this case, the drop volumes can be extremely small, such that it's possible to have layer thicknesses as small as 50 nanometers. And you can have very small feature sizes on the order of about a micron. Of course, able to inkjet insulating materials, and those tend to be UV curable materials that have thicker layers in the order of about 5 microns. A nice example of the flexibility of inkjetting is shown in the figure. This is a jet printed gasser where substrate, the flexible substrate, and the interdigital interact, and a carbon tube ink, which is sensitive to a gas, is all deposited using the inkjetting process. Along with many other applications that demonstrate the versatility of inkjetting, are described in the paper at the bottom of the slide there. And finally, polyjet. So where we contrast micro-dispensing as thick film and inkjetting as thin film, useful to contrast FDM with thicker structural type devices using this process. So the diagram illustrates there's a jetting head that will spray either a structural polymer or a support material, because this is essentially coming out as a liquid, so it's can't build freeform structures. And then material is sprayed in layers are on the order of tens of microns to 100 microns they're choosing this UV light. One of the nice features, again, because the material comes out essentially as a liquid and then is cured, get a fairly smooth surface if you compare to FDM. Feature sizes are comparable to what's achievable using an FDM process. One of the main, though, is that because you're using photopolymers, which are UV cured, they tend to have a slightly higher loss case, typically around 0.02, as compared to the thermoplastics, which can have loss tangents, which are, order of magnitude smaller than this. But you demonstrate some very nice wave structures, such as this Eaton lens, which is shown in this diagram, and many other devices are demonstrated in the two papers that are listed at the bottom of this slide. So I think it's time for me to turn it over